This time, let's have Gay-Lussac'S Law, or John Louis Gay-Lussac was a person who is credited with the determination of the temperature-pressure relationship in gases at constant volume. He deducted that the pressure of gas is directly proportional to its temperature. Mathematically, it was written that P is equal to KT. The constant here is the volume of the gas. And since there is a direct proportionality between the pressure and temperature of the gas at constant volume, the simple logic here is as temperature increases, the pressure of the gas also increases. Or we can also say that as the temperature of the gas decreases, then the pressure of the gas will decrease as well. Okay, so one of the very important applications of Gay-Lussac's law is the phenomena of cooking using the pressure cooker. Have you seen a pressure cooker, class? So we all know that the pressure cooker is airtight. So pressure builds up inside the pressure cooker as the liquid inside comes to a boil. The resulting trapped steam causes the internal temperature to rise more than what it can normally do at normal atmospheric pressure. Thus, the cooking of hard meat and fiber is done at a short period of time. So, thanks to Gay-Lussac's law. Okay, so given that P is equal to KT from Gay-Lussac's law, we can show a direct proportionality between pressure and temperature of gases at constant volume with the equation P1 over T1 is equal to P2 over T2. Now, if we cross multiply this one, we shall arrive at our working formula P1 T2 is equal to P2 T1. So with this working formula, we can actually transform it and derive four other more formulas. One formula if we are going to look for P1, one formula if we're going to look for T2, one formula if we're going to look for P2, and the last formula if we're going to look for T1. So P1 T2 is equal to P2 T1. It will eliminate P1 here by dividing both sides with P1. You will obviously have your formula for T2. T2 is equivalent to P2 T1 over P1. And we can also have our formula for P1. P1 will be P2 T1 over T2. Am I correct, class? On the other hand, let's write again our working formula. P1 T2 is equal to P2 T1. Eliminating T1 on this side. Therefore, our formula for P2 will be P1 T2 over T1. And we can also have our formula for T1. T1 will be T1 T2 over P2. So, from our working equation for Charles' law, P1 T2 is equal to P2 T1. We have derived the formula for P1. For T2, for P2 and for T1. Now, let's work on our sample problem from your book. Let's read the problem. The pressure of a nitrogen gas inside a rigid tank is 1.5 atmosphere at 30 degrees Celsius. What will be the resulting pressure if the tank is cooled to 0 degrees Celsius? So, from 30 degrees Celsius, what happened to the temperature? It actually decreased to 0 degrees Celsius. So, logically, if you're going to think of it, most probably, what change will happen to the pressure of the nitrogen gas? If it was 1.5 atmosphere at first, most probably, this 1.5 atmosphere will decrease since the temperature also decreased. And let's try to prove it. So, given in the problem was the initial pressure of the nitrogen gas, which is 1.50 atmosphere at temperature 30 degrees Celsius, but this should be converted into Kelvin again. So, what do we need to do? We need to add 273.15 or 273. So, it becomes 303 Kelvin. And the temperature changed from 30 degrees Celsius, it became 0 degrees Celsius. So, add 273. So, final temperature of the nitrogen gas is 273 Kelvin. So, we should expect that the pressure from 1.50 atmosphere will change. And what change will it be? So, our working formula, since we're going to look for P2, will be this one. Okay? So, let's solve. P2 is equal to P1 T2 over T1. So, substitute the value of P1, which is 1.50 atmosphere, times T2, which is 273 Kelvin, divided by 303 Kelvin. So, what will happen to these units? They will be cancelled out. And what's left is atmosphere. So, multiply 1.50 atmosphere to 273. Then, divided it with 303 and you will arrive at the value of 1.35 atmosphere. So, if you're going to plot down the value of the pressure, the final value for the pressure of the nitrogen gas after the temperature change into 0 degrees Celsius is now 1.35 atmosphere. So, due to the decrease in the temperature from 303 Kelvin, it became 273 Kelvin. So, there was a decrease in the temperature. The pressure, which was initially 1.50 atmosphere, decreased and it became 1.35 atmosphere. So, take note for the relationship between pressure and temperature of a gas at constant volume is directly proportional. As temperature increases, pressure increases, or as temperature decreases, the pressure of the gas also decreases.